The following is a recording of a presentation that I gave at the BayNet Amateur Radio Club BayCon 2021 conference on February 6th. I talk about the basics of VNAs and the NanoVNA in particular. Be sure to check out the links in the video description down below for the BayNet Amateur Radio Club website, as well as a link to the full streamed recording over 8.5 hours of streaming presentations from the BayCon 21 conference. Sit back and enjoy, and I'll see you at the end.
My name is Alan Wolke, W2AEW. We're going to talk about an introduction to VNAs and the NanoVNA. So why do we want to talk about this? Well, mainly because these ridiculously inexpensive NanoVNAs make VNAs accessible to us hobbyists and hams. First, we'll talk about what a vector network analyzer is, then what it's good for, and then third, we'll take a look at the NanoVNA specifically. So what is a VNA? A VNA, or vector network analyzer, if you look up the definition online, you'll see something like an instrument that measures the magnitude and phase of the reflection and transmission properties of the ports of a device versus frequency. What the heck does that mean? Well, let's break it down and see if we can make it clearer for everybody. So a VNA, it's an instrument that's used to characterize RF devices, and it used to only be used by RF engineers due to the high cost. These two up on top here, this Tektronix unit and this Copper Mountain unit, are probably $5,000 to $10,000 VNAs, and they're considered very inexpensive VNAs. This 4-port device down here, this Keysight PNA-X, can list price for about $250,000. So certainly outside of the price range for most of us hams. So another thing with VNAs is that there's a lot of acronyms and terminology that might be unfamiliar to the ham. So we're going to cover some of that as well. So the first is a DUT. So what is a DUT? A DUT simply stands for device under test. Could be an antenna, could be an amplifier, whatever it is that you're measuring. Any DUT is going to affect the signal that goes through it, as well as the signal that's being applied to it due to reflections and things like that. Now you probably remember that to get maximum power transfer, you want the load impedance to equal the source impedance. Typically learn it as load resistance and source resistance, but when we talk about RF and complex impedance, the more general case is that you want to have a complex conjugate match between the source and the load. I'm not going to get into all this complex math in this presentation, but just suffice it to say that if you want to design efficient matching networks and things like that, you're going to need to be able to measure complex impedance. And that's one of the things that the NanoVNA can do for you. The other thing that's kind of interesting is that we're going to talk about signals instead of voltage and current and things like that. We're going to think in RF terms. We think of signals as waves, that they have a magnitude and they have a phase. And one way to think about phase is that it's just a delay. Okay, so the phase shift is also essentially just a time shift in that waveform. This little moving graphic here is showing the difference between a incident wave and a reflected wave as the load is moved further away from a source, for example. So we can see it may be important to know what the phase is because that will vary depending on the transmission line length between a source and a load. So when we think about waves, may have a wave that's being produced by a source going into a DUT. Any of that signal that goes through the device is called the transmission properties of that device. And any part of that signal that gets reflected off that interface due to an impedance mismatch is called the reflection properties of the device. Now the device reflection and transmission will alter both the magnitude and phase of the source signal. And a VNA measures the magnitude and phase of these reflections and transmission properties of a device. So here's a basic VNA, this green block right here. We have a source that provides an RF signal that goes out through port 1 to a DUT port, and then any signal going through that port goes into port 2, and then any signal being reflected off of that port comes back this way. There are a set of directional couplers, or sometimes a bridge, that will measure and pick off a piece of the signal that's being sent out, that's our reference, as well as the signal that might be coming or being reflected back, and that's called our A receiver. And then any part of the signal that goes through our device will be picked up by the B receiver. So these three receivers, the A, the B, and the R, measure the magnitude and phase of the input signal, the reflected signal, and the transmitted signal. And of course, there's a little compute engine that will then take these magnitude and phase results and compute our responses and display them graphically for us. The transmission properties are based on measurements that are made in the B receiver with respect to measurements made in the R. So it's essentially B over R. And that gives us our gain or loss properties of our device, which is also known as the transmission coefficient, or S21. And we could also use it to measure the insertion phase or group delay through our DUT. The reflection measurements are measurements that are made coming back through port 1 again and picked up on the A receiver. So they're based essentially on measurements that are the A measurement with respect to R, or A over R, and that will give us things like the VSWR, reflection coefficient, or S11, or return loss, or even input impedance of our device. Now, most professional VNAs will have the source and couplers available on both port 1 and port 2, but the NanoVNA is really of this configuration where you only have the source and couplers on one of the ports. So what's a VNA good for? Single port measurements are basically you're making reflection measurements, which are like the SWR of an antenna, or complex impedance, or looking at even the impedance of components like passive components, inductors, capacitors, crystals, etc. And you could also do things like measure feed line length or distance to fault measurements with some additional mathematical transformations. Two-port measurements are the transmission measurements, what happens through a device, such as measuring the filter shape, or maybe loss through coax feed line or something like that, or a delay in a DUT, or even measuring amplifier gain and frequency response, which allows you to measure a multitude of RF devices that we typically use as hams, antennas and filters and duplexers and amplifiers and splitters, attenuators, etc. So what are S parameters? Well, I mentioned them a little bit earlier when we talked about some of the measurements, and some people kind of get confused or scared or intimidated by S parameters, but they don't really have to be. They're fundamentally fairly simple. S stands for scattering parameters. Now I know that doesn't help tell you what they are, but here's what they are. It's actually pretty simple. It's simply a ratio of a measured response to a stimulus, and that's what's indicated by the two numbers. The two numbers refer to port numbers. So the measurement of the response at port X in response to the stimulus that's being applied by port Y. So for example, S11, it's the response measured on port 1 in response to the signal applied by port 1. So in a sense, it's the reflection off of a DUT port. That's the reflection coefficient. Okay, pretty simple. That's S11. S21 is a measure of the B receiver, right? The transmitted properties divided by the reference, okay? So it's the measure of B in response to the reference signal being applied. So it's essentially just the response through a device, okay? The gain or loss through a device. It's really that simple. So another thing that comes along with VNAs is something called a user calibration. You might say, well, I just bought this VNA. Why do I have to calibrate it? Didn't it come calibrated from the factory? Well, the user calibration actually extends what the factory calibration does. And so why do we actually need it? Number one, we're measuring typically pretty large dynamic range. And so what that means is there are very small, like systematic errors that can't be calibrated out at the factory because they're dependent on how you actually use the device. So we actually have to do them in a user calibration in order to get that good dynamic range and remove those error sources. Also, we need to measure phase. Now remember we said that phase is also a measure of delay. So the factory has no idea what length cables or adapters you're using to connect the VNA to your device under test. So it doesn't know what phase shift you're going to have up to your measurement plane. Okay, so that establishes something called a measurement plane. So oftentimes you need to know the impedance at a particular point, like at the input to my device. So I need to remove the phase shift and delay and things like that in the cables going up to that. So the user calibration allows me to do that. So that's kind of another systematic thing that we remove out. So a factory calibration can account for all of these things, and that's why you need to do one. So when do we need to do a cal? We really need to do a user cal whenever we make a configuration change. A different set of cables, a new adapter, or a different thing that we're measuring, and especially when we change the frequency range that we're making a measurement over. That's when we do the user cal. So again, this user calibration corrects for these systematic errors, such as the source and receiver frequency response. Okay, the matching errors, matching at the device ports to the cables and things like that. We can remove those things as well. So, or even from our source to the port, that type of a thing. So we can remove any of those mismatch errors so they don't become part of our DUT measurement. Also, the directivity of the couplers, crosstalk between the ports. We want to make sure that those errors are not part of our DUT measurement. So the user cal measures those so it can be removed from the measurement results. And then finally, we want to remove the effects of our interconnect to our DUT, so user cables and fixtures. So we establish the measurement plane at our DUT. So all of these things are done through the user calibration. So what are some common VNA display formats? Now, most of the measurements that we make are made versus frequency. The reflection coefficient, or S11, is typically displayed as a log magnitude response. Okay, and typically it's a negative dB value because the reflection itself can't be bigger than the signal that was applied, so that it's always a value that's less than 1. So if we take the log magnitude of that, it's going to be a negative dB value. If you simply remove the negative sign in front of that, then you essentially have the value called return loss. But the VNAs typically will show it as the log mag of S11, which would be a negative value, but just invert that without the sign, and that's return loss. The SWR is typically a linear value like 2 to 1, 1.5 to 1, etc. Complex impedance is most often displayed on a Smith chart. You do have options of displaying real and imaginary components versus frequency, but a Smith chart is a more common way to actually go take a look at that impedance. And then the transmission coefficient, or the gain or loss through a device, is again typically represented by the log magnitude response. I've got 10 dB of gain, 5 dB of loss, etc. And then the insertion delay, the phase, group delay, things like that are typically on a linear scale. And of course, there's a time domain transform measurement that allows you to make measurements versus time, which are typically used to measure the distance to fault or the length of a cable. And it's typically measuring the reflection coefficient, but if you change it to linear, you actually get a sharper peak in the response. It makes it a little bit easier to get a precise measurement of delay or distance. So now that we know what a VNA is, let's now take a more specific look at the NanoVNA. And unfortunately, there are several developers and variants of the NanoVNA. It's not like buying a device from MFJ or Rig Expert. The NanoVNA is kind of an open source project, and there's lots of different manufacturers and variants that are out there. So I'm going to cover some of the more popular ones. The original was also called the NanoVNA H, came out with a little 2.8-inch display, smaller than a credit card. It didn't even have a case on it, just had some plates on the top and bottom. Later on, there were devices with a nice molded case. But that tiny display, for guys like me, I'd much rather have a larger display. So the same developers did a 4-inch version, it was called the NanoVNA-H4, and that's got a 4-inch display, nice molded case. This is what I'm going to base most of this presentation on. It's the one that I use most often here. It's actually a pretty nice device, and $60, can't beat it. There's also a -F version, a NanoVNA-F. Based somewhat on the same design, but the developer of that kind of went a little bit different direction. He used a metal case. He actually properly named these ports, port 1 and port 2, instead of calling them channel 0 and channel 1. He did some nice other things with the graphics in terms of adding scales to it and stuff. Again, in a nice metal case. But it's about double the price of the H or the H4, but it is a nice unit. The V2 or SAA2 goes up to a higher frequency, up to 3 or 4 gigahertz. The initial versions of that didn't have a case, just had kind of a stacked set of boards and a couple of plates. But then as of about like January, when I'm recording this, January 2021, I still like the H4. It's stable, you get good support, it's easy to get, it's inexpensive, and it works really well for what we want to do as hams. The SAA2 and now is also now available in a 4-inch version with N connectors. It's called the SAA2N, and works pretty well. It weighs several times more than the H4, but actually works pretty well. And in these same folks that developed the V2, the most recent one they've got is the V2 Plus 4. The V2 Plus 4, kind of shown here, is about $130, but up to about 90 dB dynamic range, which is pretty amazing for about $130, $140. So a couple more details on the NanoVNA. All of them are 2-port, 1-path, meaning they've got a source only on one port. The H4 goes to 1.5 gig. As I mentioned, like the V2 plus 4 goes up to about 4 gig. They all offer standalone operation with a battery that lasts a couple of hours, but they also all offer the ability to connect up to a PC or sometimes an Android device and use some external software to get some enhanced plots and things like that. NanoVNA.com is a good website resource for all the original versions, and also a link to kind of the very active user group that's there. And then there are separate websites for like the V2 versions, and that can be kind of found here. This nanorfe.com website will get you all the supported information for the V2s. So under the hood of the H and the H4, this is kind of what it looks like from a block diagram schematic standpoint. Channel 0, channel 1, that's effectively port 1, port 2 from a VNA parlance where your DUT gets connected. The RF source is this serial bus controlled RF synthesizer, an SI5351. A bridge is used to separate out the transmitted and reflected signals to basically, when we have an impedance mismatch, we'll get the essentially reflected signal coming back. We have 3 mixers, very common Gilbert cell SA612 mixers that are used to convert the RF, reflected, reference, and through signals, so essentially our R, A, and B receivers, down to audio signals, which then go into a stereo audio codec that uses some high resolution analog to digital converters to sample the responses from all of these mixers. And of course, there's a microcontroller that controls all of this, collects all these results, computes the results, and puts them out on the LCD display. The user interface is pretty simple. There's a jog wheel in the top that allows you to rock back and forth to things like move markers or move up and down on menus, and then you can push it to either initiate or select items in the menu, things like that. There's also a touch screen that allows you to touch the menu items to select them, as well as touch and slide to move markers back and forth. Fairly simple menu structure to go through. The display menu leads you into being able to select traces and put them on different channels, and then select the format. And then there's markers and stimulus and cal, etc. There are save slots for the calibration and setup so that you can recall them later on. And there's also a USB port for both charging and the PC interface. A couple more details on the calibration. Most of the VNAs are just 101 points per sweep. So what that means is a wide frequency range is going to have a fairly coarse spacing between the calibrated points. But if you calibrate over the frequency range you're measuring, that's fine. But if you later change the frequency range, the VNA will try to interpolate between those calibrated points. But you don't want to calibrate over a gigahertz and then measure over 1 megahertz, because you might not even have 1 point sitting inside that measurement range. So it's always a good idea to calibrate over your frequency range. Now, I had a little asterisk here because there are some other versions of firmware available for a lot of the VNAs that will increase the number of points up to even as many as 400 points, or using the external software you can actually get more points as well. So the VNA calibration indications on the screen appear over on the left-hand edge. The capital C indicates that you're calibrated over your current frequency range. You're good to go. The small letter C means that I've got a calibration loaded, but it doesn't match the frequency range you're measuring. And then the number indicates for the current calibration we're using what slot it's stored in. The D, R, and S are for all of the channel 0 calibrations, okay, indicating that they've been applied. And then, or corrections have been applied, and then the T and the X stand for the transmission and crosstalk error corrections being applied for channel 1. These first 3 are needed for all the measurements you're going to make. The second 2 are only needed if you're making transmission measurements. So if you're not making transmission measurements, you can ignore that portion of the calibration process. And this is the process. It's actually pretty simple. Go from the main menu, you hit Cal, and then Reset. Once you hit Reset to clear the current calibration, you hit Calibrate, and that will bring up this menu on the side here, prompting you to attach the open to channel 0. You do that, touch open, and then you do the same thing for short and for load. And that, again, this is required for doing all measurements. If you're going to be doing some through measurements, then you want to also then do the isolation and through calibrations by attaching the load to channel 1 and then connecting or channel 0 to channel 1, do a through, hit done, and then you can select what slot you want to save in. Now, if there's something that you're going to do most commonly, you can actually save that result to slot 0, and that's always recalled on power up. So the thing could power up right the way that you want it. Connect all of the CAL standards when possible to the same place where your device under test will connect. By doing that, you can ensure that you've established that measurement plane right at your device interface ports. Now, in those cases where you can't connect exactly to where your device would connect, to be able to remove the phase of those interconnections, you might need to use an adapter or some other length of interconnect out to where your device is. So you can actually use this feature called port extension to essentially slide that measurement plane back and forth to establish it at your particular spot that you need on the DUT. This can be done on the NanoVNA. It's actually called electrical delay instead of port extension. And you can actually do it on the Smith chart, for example. So like you had an open on the Smith chart, that would normally appear here. But if I change my interconnect length to where that open appears or where my DUT is going to appear, it might rotate around the chart. You would then adjust the electrical delay to slide that point back up to the perfect open location. And again, this is only important when you must have an accurate phase measurement or must establish a measurement plane that is not easily accessible by where you would connect your standards. Now the NanoVNA has got two channels, right? Channel 0 and channel 1, and can have up to 4 traces. The channel 0 again is the reflection channel where you're measuring reflection coefficient, SWR, input impedance, etc. Channel 1 is your transmission port where you're measuring the through response of a device, S21, loss and gain, etc. That's kind of selected down through this menu structure. So essentially go to display, select traces, select a particular trace, then tell it what channel you want it to be on. You can have any number of traces up, 1, 2, 3, or 4, and each of those traces can be assigned either to channel 0 or channel 1 for the reflection measurements or through measurements. Common trace formats are typically shown here. You go to display trace, then select format. The channel 0 measurements, you're most often using either log mag for S11 or a Smith chart to look at complex impedance or selecting SWR. For the channel 1 measurements, again, it's typically log mag for the loss and gain measurements. Then you've got phase measurements, which are typically going to be linear, and then the delay measurements are typically linear as well. And there's other additional measurements that are available here as well for more advanced applications typically, but there's a lot of other ways to display the same data. It's all just mathematically related. Setting the source or the stimulus is setting the frequency range you're going to make a measurement over. And you basically pick whichever is easier. If you're measuring over a particular amateur radio band, you might want to set the start and stop frequency. If you're measuring a filter, it might be easier to select the center frequency and the span. Just use whichever one is the most convenient for your application. And you also have the option of measuring at a single frequency without doing a sweep, and that's the CW frequency. There are up to 4 markers available to you. You can either drag them with your finger or a stylus on the display, or use the jog wheel to move them around. And you also have the ability of getting a delta measurement from the last 2 markers you've selected. The selected marker is shown here. The marker values are kind of shown on the lines right after each trace description. So here the yellow trace is channel 0, it's log mag, so that's the log mag of S11. The vertical scale is 10 dB per division, and where the active marker number 2 is, right here, that's minus 8.19 dB. So that's how you see that. So the delta says that this is the delta from marker number 1. So that's the difference between where marker 2 is and where marker 1 is. All the markers track each other on every single trace. So you can have up to 4 traces. So one marker will appear in 4 places. They all track each other as you move around. There are search features to search for like min and max on the traces, for example, and then operations that allow you to do things like set the start and stop frequency based on where markers are. It might be convenient to kind of retune the analyzer. And of course, you can set the units that are used for the Smith chart measurements as well. So the basic process to set up the NanoVNA is to start by configuring the traces, what channels they're going to be on, and what formats they're going to have. And you set up the stimulus to measure for the frequency range you want to measure. The order you do those in really doesn't matter. Okay, once you've done that, then you can set up and do the calibration and save that. Then you connect up your DUT and run your tests, and maybe you put some markers on there and make some measurements and understand what's going on. And you can even make some changes to the traces and formats if you want to kind of look at things different ways. But that's the basic process of using the NanoVNA. So let's look at a couple of quick examples. So here's an example of measuring an antenna. I've got an antenna connected to port 1, which is channel 0, which is the S11 port. Okay. So the frequency range is shown down here. In this case, I've got a start frequency of 7 meg, a stop frequency of 7.3. Okay, so I'm measuring over the 40 meter band. So this blue trace right here, or the cyan trace, is my SWR plot. We can see up here it's on channel 0, so I know it's the reflection port. It's SWR format. The vertical scale is 1 per division, so that means that I'm 1 to 1 down here, 2 to 1, 3 to 1, 4 to 1, etc. The marker I didn't move, so it's sitting right at 7 megahertz. So we can see that, for example, at 7 megahertz, the SWR of my antenna was 4.73. It goes down to about 1 to 1 up here. That's probably about 7.2 something, 7.25 megahertz or so. I've also got the complex impedance shown on the Smith chart. That's on the circular chart here. Okay, there's the values where the marker is right now. And then here's the log magnitude of the reflection coefficient. Okay, that's the yellow trace. It's yellow up here and yellow right there. And of course, the minimum for the S11, the log mag of S11, coincides with the minimum for the SWR. But that's typically what an antenna measurement would look like on the NanoVNA. So if we want to measure something like a filter, in this case, this is a low-pass filter that I designed to put on the back end of a Michigan Mighty Mite homebrew CW transmitter. So I've got the frequency range from 1 meg to 15 megahertz in this case. The insertion loss of that filter is shown by the blue trace here. So that's channel 1, doing the log magnitude of that. So I can see I've got about 0 dB of attenuation in the passband here where my fundamental is. And then we up around 4.5 megahertz or so, it starts coming down. I got the marker here sitting at about 10.5 megahertz. So that we can see that my filter response is down about 47 dB down at where about the third harmonic would be. So I'm getting good third harmonic suppression out of this filter. I've also got the SWR looking into the filter. It's nice, below 2 to 1 up through the passband, so that's good. I've also got the reflection coefficient shown in here as well for the input to the filter. Again, just a mathematical derivation off of the SWR. And of course, I left the complex input impedance on there, but didn't really need it from this particular case. Measuring coax length or distance to fault, this is where we use the time transform function. It's still a measurement on channel 0, but now the x-axis turns into time. And if we tell the NanoVNA what the velocity factor is, any of the marker measurements can actually be converted to distance. So in this case, I had about a 9 meter cable connected to the VNA. Now, of course, if we don't use the time transform and we connect the other end to channel 1, we can actually measure insertion loss of the cable versus frequency, which is S21, similar to the process we used to measure a filter on the previous slide. A little bit of the good, the bad, and the ugly, the limitations and downsides of the NanoVNA. So only 101 trace points. So again, external software helps this one, as does some third-party software. And like I said, the NanoVNA V2 has got 200 points. On the H and the H4, the output is not a sine wave. It's actually a square wave. It's shown right here on the scope. Okay, and it only goes up to 300 megahertz. Above 300 meg up to 900 meg, the VNA uses the third harmonic to make all the measurements, and then above 900 up to 1.5 gig, it uses the fifth harmonic. So this 200 megahertz square wave that's shown right here is the same output that you get if you were measuring at 600 meg. It's the same output that you get at 1 gig. We just are using a different frequency range in making the measurement. So that may, do you have to think about, is that going to affect what I'm measuring? Is the device I'm measuring, is that going to care the fact that it's getting hit with a square wave that has this harmonic energy or not? So you have to think a little bit about that. And the output power, the output amplitude of this is not adjustable. So it's about a milliwatt, about 0 dBm at the fundamental. It's about 10 dB lower at the third harmonic, about another 10 dB low, 10 to 12 dB lower at the fifth harmonic. So again, is that going to be correct for the device you're measuring? Because you can't really adjust it. It also means you can't do things like gain compression measurements and things like that on an amplifier. Also, the receive reference level is not adjustable. So if we are measuring an amplifier, I would probably then have to pad down the output so that by the same amount that the amplifier brought it up, so that I would get about the same amplitude going into the VNA to make an accurate measurement. And limited dynamic range compared to professional units, but again, adequate for most of what we're going to do as hams. And also the resolution bandwidth of the measurement is typically not adjustable. Some third-party software and firmware does allow you to make some adjustment to that. But again, there may be some other limitations as well, but those are probably the more common ones that you're going to run across. So in summary, the NanoVNA, I call it the RF tool or toy of the year. Pretty fantastic capability for what you get for about $60. Lots of videos and resources online to learn how to use it. I've got a nice playlist on my YouTube channel that talks about some of the more common measurement applications. So some pretty active user groups, very helpful and very active that you can go look at and get your questions answered. And again, a good US source for a lot of the versions, but not all, is Arendelle Electronics. That newest version that I mentioned, that V2+4, is not available through Arendelle. It's only available through some of the Chinese distributors.
So I hope you enjoyed that video. If you did, give me a thumbs up. If you haven't subscribed to my channel already, please consider doing so. And again, be sure to check out the links in the video description down below for some more information about the club and the conference that this presentation was prepared for. Thanks again, as always, for watching, and we'll see you next time.